Okay, am I audible to all of you?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Okay, maybe page is also visible.
Yes, yes.
Yes, ma'am, it's visible.
Okay, fine. So today we'll start with infrared spectrophotometry. Okay, and along with that, we also have to cover another unit, which is Raman spectroscopy. That also we have to take care today. So in the last class, we discussed what is your electromagnetic radiation and how it is getting interacted with the matter and various windows regarding various windows, slots and spectroscopic method. We discussed glimpse of that. Little bit we touched all the spectroscopic parts. But last class, in the second unit, we had discussed UV visible spectrophotometry, UV visible spectroscopic method in detail, and what type of transitions can be there, what is Beer-Lambert's law, and how you can apply it. So, in short, I had discussed everything with you. So today we'll move to the another part, that is infrared spectroscopy. What is that thing? In the last class, I was telling you, when the radiation of infrared region radiation is falling on matter, that time the vibrational aspect of the molecule takes place, and that part of the things we can study through infrared spectroscopy. Like I was telling you yesterday, that all molecules will not show you UV visible. All molecules will not show you IR or Raman microwave. There is some specific characteristic with the molecule that is very, very essential. First thing is the molecular characteristics or feature is very important. Second thing is the radiation which is getting fall on the matter, that is also important. Okay. So based on that only different segments of spectroscopy is there. But if you really go deep into this thing, then IR spectroscopy as such will take 14 classes. IR spectroscopy, so much is there. Means depth of that and net get oriented questions, you will get many questions out of spectroscopy. So now we'll start with the topic of today's part, that when IR radiation is falling on matter, you know the bond between two atoms in a molecule is not rigid. In physics also you might have studied simple harmonic oscillator, right? So it has some elasticity, okay? And as a consequence, the atom in the molecule do not remain fixed in their position. It will be just moving type. Okay, it is not fixed at its position. And as the transitions between these quantized energy levels can be brought out by using electromagnetic radiation in the infrared range, it gives rise to an IR spectrum. Means it is saying that there is vibrational energy level transition. Last class, if you remember, we were discussing there is electronic energy level transition or vibrational level transition or rotational energy level transition. Okay, so it gives rise to your IR spectrum. As the excitation among the quantized vibrational energy levels of the molecule is involved, so the IR spectroscopy is also known as vibrational spectroscopy. So don't get confused if the question is coming, write the basic principle of vibrational spectroscopy. You'll confuse, okay, I have studied IR, from where vibrational is coming into picture. But vibrational spectroscopy is also is your IR spectroscopy. So these vibrating diatomic molecules, they behave like simple harmonic oscillator. Okay, so both the side they will be swing evenly, and the bond which is in between that is considered to be like a spring. In plus 2, you might have studied the simple harmonic oscillator. Here in your course, it is not there in detail. Just to remind you, I am just reminding that you might have studied the Hooke's law. There is certain force and there is displacement of these bond molecules, and they will be moving or swinging in both the sides. They will be swinging in a particular place. But there is internuclear distance, that is R, internuclear distance, or you say equilibrium distance, along which this side it will be swinging evenly and that side it will be swinging evenly. Okay. So the real molecules, in practically, if you see, the real molecules are not like harmonic oscillators. So these sometimes they face the unharmonicity. So basically, you may get question like, what is the difference between harmonic oscillator and anharmonic oscillator? Okay, so this difference you may get as a question wherever you see. How to differentiate the harmonic oscillator? If you see these two graphs, graphs A and B, you see the energy profile of it. Why I reminded you about Hooke's law? Because there the energy expression of the simple harmonic oscillator is of a parabolic expression. So we are getting a parabolic shape here, the energy versus your internuclear distance in nanometer. So you see this one, this thing is evenly spaced. So you can see the lower red one and the upper red ones evenly spaced, means harmonic oscillators, the energy gap, energy level separation is even, equispaced. The quantized energy levels are equispaced. However, if you see this anharmonic oscillator part, then it is no more equispaced. First point is that it is no more equispaced. Second point is that you see, as you go up, you can see the spacing between the energy levels is also decreasing. The spacing between energy level is also decreasing. And another difference you will be seeing, see, there is bond breaking. It is no more even parabola. So a point will come where bond will dissociate. There will be bond dissociation for real molecules where the energy is now no more there and bond dissociation happens. Here in this figure it is not clearly mentioned, but this energy is known as dissociation energy. D0 is a dissociation energy. So this is the harmonic and unharmonic oscillator. But as I was telling you, which kind of molecules will show the IR spectroscopy? So question may come in this way, that what are the necessary condition for observing IR spectrum? Or else, what is the basic of IR spectroscopy? Or what is the basic principle of IR spectroscopy? Question can be in either way. The basic things you must know: what kind of molecules will say, and what is its selection rule for the IR spectroscopy to happen. Okay. So the presence of quantized energy levels doesn't ensure your transition amongst them when the radiation of appropriate wavelength fall on it. As I was telling you, every radiation will not bring about the IR spectroscopic part in a molecule, or you cannot study that molecule through IR, you cannot study through UV visible. There should be the radiation of appropriate wavelength should interact with the matter. That is the first condition for every spectroscopy. The first point is this one. The radiation of appropriate wavelength should fall on the matter. Okay. And here, for the IR spectroscopy to happen, the vibrating molecule or the molecules, it is essential that the molecule has a fluctuating or oscillating dipole moment. It must have a oscillating dipole moment. Okay. For example, a homonuclear diatomic molecules like H2, okay, or O2 that are inactive IR spectrum, they will not show because they don't have permanent dipole moment or fluctuating dipole moment. However, it it doesn't generate fluctuating dipole moment. However, if you see HBr or HCl, HF, these things will show you dipole moment. So they absorb the IR region radiation and they will show a IR spectrum. Okay, so this kind of molecules you can study through IR spectroscopy. So the molecules which are having oscillating dipole moment can be studied through IR spectroscopy. What is the selection rule for vibrational spectroscopy or IR spectroscopy? This is also coming under the basic principle. Like the way I was telling you, this is the point one, appropriate to wavelength radiation should fall. Second point is the essential that the molecule has fluctuating or oscillating dipole moment. Then your third point is the condition that tells us about the transition that are possible, that is allowed transitions among the quantized energy level. The selection rule is saying the delta V, delta V should be plus minus 1, plus minus 2, plus minus 3, like this. If you see here this diagram, then the vibrational energy 0, the ground vibrational energy level, then vibrational energy level 2, 3, then upper parts. So the first transition, that is V0 to V1 transition, that will show you the fundamental band. That will show you the fundamental band in your IR spectrum. However, when you are getting the band due to V0 to V2 transition, you are going to get first overturn. Similarly, you are going to get second overturn when there is transition from V0 to V3. Subsequently, third overturn, like that. But always the fundamental bands are more intense as compared to your first overtone and second overtone. Overtones are less intense and you get the weak signal due to these overtones, and fundamental band is of large intense. If you remember, I was telling you about the Boltzmann distribution. So population and how the number of molecules getting transited is also playing a role. So all the things are interlinked among here. So this vibration of polyatomic molecule, if you see, when diatomic you are saying AB type, it is easy. You are saying it is simple harmonic, yeah, this, that, all that things. But vibration spectrum of a polyatomic molecule with a number of bonds when it is having, it is quite complex. So that time you need to calculate how much vibrational modes are existing with that molecule. Remember, you will be getting net gate questions quite often due to this vibrational mode calculation. Okay, if you see for a linear molecule containing n atoms, so if I'll give you problem now, so just understand it. If you are having n atom in a molecule, then you will have for a linear molecule 3n minus 5 number of vibrational modes. If you are studying nonlinear molecules, then you will have 3n minus 6. Okay, 3n minus 6 vibrational modes. So for CO2, how many vibrational modes will be there for CO2? Here it is
4.
mentioned.
4.
It is 4. And for water it is
3. 3.
3. Okay. Just tell
3.
me for n taken how much it will be. I'm just seeing whomever are answering. For n taken, what will be the number of vibrational modes? Tell me any answer.
19
19.
only.
No. For n decan.
Yes, ma'am.
No. n decan means कितना हुआ? C10
C10
is
H22.
22. Okay.
Yes.
Then n will be how much?
32.
N. Okay. Then your
32 into 3.
3. It will be 3n minus.
6.
Then
Then it will be 90, ma'am.
yes. So it is 90. Then for CH4, no one is answering here.
9.
Write in chat box.
Ma'am, it will be 9.
CH4. So we are dealing with CH4 is non-linear or linear.
Non-linear.
So you will have uh, who is asking? Are he sees Angshika. You are seeing the screen. In screen, I am not teaching now. I am just giving you problem, and I am waiting the chat box who is writing what. Okay. So no one is writing in chat box. So again, I am coming back to the study. So your CH4 is non-linear. So accordingly, it is your 3n minus 6. Okay. So this kind of questions you can expect in NetGet. So how many number of vibrational modes you are expecting, so that you can find out. Okay. So there are basically two type of normal mode of vibration. Basically, in the broad way, if you categorize, then you will have stretching vibration and bending vibration. Okay, stretching vibration are of two type again: symmetric stretching and anti-symmetric stretching. Okay, so anti-symmetric stretching, you can see here, means if you pull your hands to a single direction, then you are going to get anti-symmetric stretching. One will be coming towards the molecule, one will be going away from the molecule center of part. Okay, if you are seeing the symmetric stretching, then evenly you will be pulling your two hands and your body will remain intact. So bending, there is out of plane bending as well as in plane bending. This is the example we are seeing for the linear triatomic molecule. Okay, and for angular molecules also you can see this kind of thing: symmetric stretching, anti-symmetric stretching, and bending portions. Okay, so whomever joined late, they should know that we are studying the IR spectroscopy. Joining late is also very dangerous for you people, because from the beginning, who is not able to catch, later on subsequent two classes he or she may not understand. So that is a problem. So always try to join in time. I think whomever joined late may not be able to understand the thing, because all are interlinked. So bending vibrations, there are many, like scissoring, rocking, wagging, twisting, this kind of bending vibrations. You can imagine yourself that if you are having this is your twisting, means both the bonds AB2 molecule. Okay, both the bonds will be in twisting form. Then scissoring means like a scissor. You are just scissor. You can imagine the two bonds you are just bringing close to each other. This one is scissoring. So these are the bending portions, and the antisymmetric, symmetric stretchings are there. But The complexity part with the IR spectroscopy is polyatomic molecules when you are dealing with. I was telling you yesterday also, if you coordinate the things, it is not so easy for a molecule. We are saying, okay, let us see the 90 vibrational modes will be there. Am I going to get 90 peaks? 90 bands? No, not exactly. I may not get that. The complexity with this is the IR spectrum of a polyatomic molecule would consist of an absorption band at each of the 3n minus 6 or 3n minus 5 fundamental frequencies for linear, nonlinear and linear molecules respectively, along with the corresponding overtones. You'll be getting fundamental bands along with the overtones. In addition to that, you may get some weak peaks due to the combination of two fundamental bands. That is called combination bands. Or you may get the difference of two fundamental bands. You may get difference bands, or when sometimes the fundamental and nearby weak overtone have same frequency matching close to each other, then they may resonate, leading to appearance of another signal. Frequency is higher or lower relative to the original position is called due to Fermi resonance. Fermi resonance peak you may get. So you are going to get a lot of things like fundamental absorption, weak overtones, combination band, difference band, Fermi resonance band you may get. So here I was asking you about the endecan C10H22 having your 32 atoms. So we calculated it to be coming the vibrational modes 90, but along with the corresponding overtones and combination bands, the spectrum is expected to come like few hundred signals. 90 plus overtones will be there, combination small bands will be there, so 100 plus we are expecting. However, the actual spectrum has much fewer of them. It is less than the 90 even, because this is because all the vibrations may not be IR active. Which vibrations will be IR active? If that vibration is leading to change in oscillating dipole moment within a molecule. Just imagine symmetric stretching. Do you think symmetric stretching will bring the change in dipole moment? No, because it is symmetric stretching. Change in dipole moment, net dipole will not be there. It will be zero. So that will be may not be IR active, but the vibrations which lead to change in dipole moment, that only will give you, that will be IR active. That vibrational modes will be IR active. But when you see the IR spectrum, coming to the IR spectrum, last class we studied the UV visible spectroscopy, where your y-axis was observance, right? Y-axis was the observance, but here the y-axis is your transmittance, and your x-axis is represented in terms of wave number, and these all are your vibrational peaks you are getting at different wave numbers. Last class we are discussing your wave number is just inverse of your lambda. Okay. So IR spectroscopy is represented by, the IR spectrum is represented by transmittance and the wave number. Okay. Transmittance, yesterday I was telling you what is your transmittance. So you are going to get many peaks here. So these are the questions you can also see. So the basic components of IR instrument, if you see, Last class we were discussing there must be a source of radiation, there must be a sampling device. Okay, sampling device should be there where you are going to keep the sample, then a monochromator or frequency modulator which you say, then detector will be there, then your signal processing or output device will be there. Yesterday also we discussed regarding UV visible part, but today we are going to discuss IR radiation. Yesterday, if you remember, for UV visible instrument, absorption spectrophotometer, there we used the source as the what? Deuterium and tungsten lamp. Okay, and tungsten halogen also. Tungsten halogen will cover all the things, but here the source of IR radiation are your nonst or glare filament lamp, glovar, nickel chromium wire, carbon dioxide laser. This all can be used as a your IR source radiation. Okay, sampling device, if you see, uh, just let me show you. Just a minute, give me a minute. I'm just bringing the cuvette and show you the cuvette, how it looks like. The cuvette are the quartz cuvette, right? Quartz cuvette we discussed for individual spectrophotometer, we use quartz cuvette. But here the sampling is very different. Just a minute, I'm just opening my video to show you. Okay. See this one. Are you able to see this? This is the sample cuvette. Okay, where we are going to take the liquid sample for studying your UV visible or fluorescence, phosphorescence parts. This is the sample cuvette of 10 mm path length, 10 mm path length. For biosamples which are very costly, we generally take this half away. Okay, this is the sample cuvette where you can keep your solution and you can use it. This is made up of quartz. So basically, we can take quartz cuvette or polycoated cuvettes also for the studying your UV visible part. Mostly quartz cuvette we use. But if you see your sampling method for IR spectroscopy, it is very different. It is very different. Just I am showing you that sampling technique. Okay, just let us move to that part, sampling method. So here, handling of sample for measurement of IR spectra is not that simple. Fastly, because unlike your UV visible spectrophotometry, where glass or quartz cannot be used as a material for making cuvettes to be used in IR region, you can't use glass or quartz cuvettes for IR region radiation to fall on it. It is because the glass absorbs strongly at most of the frequencies in this region, in IR region. Secondly, analyzing an analyte as a solution is not easy because most of the solvents that are organic compounds, organic solvents, themselves also observe many regions of the IR spectrum. So these are the shortcomings of using glass or quartz cuvettes in IR spectroscopy. So what then we'll use? So in absence of glass, the salts like your NaCl and KBr, which are transparent in IR region. Most important is they are transparent in IR region. They will not absorb. the IR radiation, and they will not interfere in studying what sample you are going to study. Okay, so these are used for the construction of cuvette. So the cuvettes made up of this initial and KPR are used for studying the IR spectroscopy, not the quartz or glass cuvettes. So these cuvettes are called IR windows. These are called IR windows. However, these NaCl windows are most commonly used for routine work in the region of your 4000 to 650 centimeter inverse, as these are cheaper than your KPR windows. However, if you want any measurement which is below 650 centimeter inverse, the KBR cells are the right choice, because this NaCl windows doesn't observe in the within the 650 region, but it will observe below this. So better to go for the KBR windows while choosing your below 650 centimeter inverse scale. Okay, so how the sampling happens here? These are the sampling of gases. Here you can see this A compartment which I have mentioned here figure, that are mostly used for the gaseous samples. You can fill the gaseous samples inside, and both the ends there will be sodium chloride windows. Okay. But however, if you are seeing the liquid sample, the sample technique B, for the liquids, the cuvettes with fixed path lengths as well as variable path lengths are available, and the cuvette of less than 0.01 mm thickness are made up of your sodium chloride and potassium bromide. A drop of liquid, you can see the figure B, the middle part, middle compartment, a drop of liquid is squeezed in between your NaCl or KBr plates at both the sides. Then you can go for the scanning purpose. So this is the sample, how you are going to take the samples. But mostly, wherever you go, mostly solid samples are basically used for the IR spectroscopy, and these two techniques are mostly used. One is mole technique, another is paletting with KPR. Quite often in FT IR spectroscopy, we use this paletting of KPR technique, paletting method. Here you can see the mole technique. In this technique called nozzle mole technique, the sample is finely grounded to a paste in small amount of mineral oil to make the paste, which is known as nozzle. That is why we say nozzle mold technique. It forms a fine suspension, or that suspension we call this as mole, okay, of the sample in oil. Then that mole is pressed in between the NaCl KPR plates to give a thin film of the sample. You understood? Now the sample is in form of a paste which is called mole. Then both the side NaCl or KPR plate, depending on the web number where you are going to study, press it in between that so that it will form a film of that sample, and the two plates are then clamped in holder with the open windows on both the sides. Then you can go for the irradiating with the IR beam. Then KPR pelleting, how you are doing KPR pelleting? That in this technique, a small amount of sample, that is near about 2 milligram, within 2 milligram, is mixed and ground with about 100 times of its mass of potassium bromide. It has to be very, very finely divided. The mixture is transferred to a evacuable dye to remove the moisture. Moisture should not be there, it should be moisture free. Then a high pressure is applied to yield a transparent palette. So that paletting technique is very, very important. So while dealing with this spectroscopic method, you might be knowing you must need a technician. If not PhD scholar, if not a research scholar, there is appointment of the technicians too. So chemistry is having lot of opportunity. Don't stick to a particular thing like your professor or lecturer or anything. If you are not able to, due to familiar reason, if you are not able to study much high part, then also if you are having this much knowledge, also you can apply for the technicians whomever are handling these things, or we may say assistant, research assistant appointments. So it is put in a suitable holder, or a whole assembly is placed in line of, then irradiate with the infrared beam. Okay, so that also you can do. So basically what is happening, you are just making the pellets and irradiating with the light beam. Okay, then your monochromator or modulator is coming into picture. Last class also you saw there will be monochromator. So monochromator is an optical device that transmits a selectable narrow band of wavelengths of radiation, chooses from a wider range of wavelength available at the input part. Okay, so in the IR spectrophotometer, we use similar component, that is monochromator, but the difference is it is placed in after the sample. It is placed after the sample to collect the radiation that is passing through it. Then you will have detector which will detect that radiation which is coming out of that. You might have last class we saw there is photomultiplier tube, then other detectors are also there, but here we are using thermocouples or pyroelectric transducer, photoconducting transducer as the detector, which is going to detect what quantity of radiation is getting away or transmitted away out of that sample. Then that thing you will have a signal processing unit or output device, which through which you are going to get the spectrum which I was showing you in the first few slides. Here it was there. Then you are going to get this kind of spectrum where your y-axis is transmittance and your x-axis is your wave number. Okay, so this is the thing. But here if you say instrument of IR spectrophotometry means measurement of IR spectroscopic method, measurement of IR spectrum which you are going to get. The IR region of electromagnetic spectrum spreads from wavelengths of zero point 0.8 to 1000 micrometer. However, we mostly designate in wave number, so it is roughly around 1200, 12,500 to 10 centimeter inverse, and it is bounded by the red end of the visible region. Here you can see this speaker. It is bounded by the red end of the visible region and at lower wavelength range of the microwave region. So it is in between your UV visible region part and microwave region part. Okay. So again, this IR region is divided into three parts. That is near IR, which is close to your visible region part, then your mid IR region, then your far IR region. So few components or few molecules can be studied in the far IR region, few will be in the near IR region, and few will be in the mid-IR region, depending on the your nature of that molecule. Okay, so there are basically three type of your instruments: your dispersive IR spectrophotometer, then Fourier transform infrared spectrometer, non-dispersive IR spectrometer. Okay, everywhere you will be seeing the the basic we are seeing. There will be a source, then out of that source there will be uh, uh, from source the IR radiation will be falling on reference or sample, or UV visible radiation is falling on a reference or sample. Then it is going to another segment. Either there will be mirror or there will be filter, depending on the resolution, how quality thing you are going to get, how today's class is audible to you, not audible to you. Accordingly you are tuning your mic or you are saying me to get a clarity. So accordingly, depending on the clarity and resolution, how the signal to noise ratio will be minimized. Then you are having a monochromator, then a transducer or detector, then amplifier will be there, so that you can get a good spectrum or good resolution spectrum of IR spectrum or your UV visual spectrum, whatever it may be, but you are going to get that. Okay. So the advantage of this IR spectroscopy is the spectrophotometer what we are using is, as the absorption at all wavelength is recorded at a time, this saves a lot of experimental time. Then this is called your multiplex advantage. Okay, you are putting all the wavelengths, you are not selecting a single wavelength by putting a monochromator from the beginning. This is lead to a spectrum with better signal to noise ratio. I was telling you, to have a good signal to noise ratio, if noise is coming less, then it's good, right? Signal will be of more intense, so signal to noise ratio should be less for the spectrum we are getting. So these are much faster, and a given spectrum can be taken in less time scale region. Okay, so these are the some others advantages written here. But coming to the application, which is also important to know how you can use this IR spectrophotometry. The thing is, we are discussing the part of UV visible spectroscopy in the last class. Qualitative use for UV visible spectrophotometer is less, qualitative use. But quantitative use is more, because if you are using a unknown sample, you can predict how much amount of analyte is there, how much quantity of analyte is there. By means concentration, you can find out. This IR spectroscopy is widely used both in research as well as industry as a simple and reliable technique for the measurement, quality control, and monitoring the dynamic processes involved. Okay, IR spectroscopy is basically used for your qualitative, quantitative, as well as other applications parts. Okay, how you are going to use this? For the structure elucidation of organic molecule by which is not completely in your course for the time being, for the PGDSC course in this class, structural elucidation. However, while studying your PG, you might have studied, or whomever are in UC, they will be studying in the classes, that structural elucidation is very, very important for IR spectroscopy. I'll give you a general idea about that, the structural elucidation, how you do. The region of spanning between your 3600 to 1200 centimeter inverse is called the functional group region. Okay, but below 1200 centimeter inverse, it is called fingerprint region. Fingerprint region. These two regions are very, very important. One is functional group region, where you are taking a organic molecule, it's having certain functional groups. You want to identify the groups involved in that, or you want to do structural elucidation. If you have synthesized a molecule, if you have synthesized a molecule in laboratory, you don't know whether your hand is good enough to synthesize that molecule or not. You want to cross check it with the spectroscopic method. By using spectroscopic method, so you have to do the structural elucidation. Later on, I will show you one table where you can find out what is that. So functional group region is 3600 to 1200 centimeter inverse, and below 1200 region is known as fingerprint region. Like two molecules A and B, they will be looking like a similar thing, but like one's fingerprint is not matching with another person's fingerprint. Twin, both are suppose A molecule and B molecules are twins. They may give you similar things within the 3600 to 1200 in the functional group region. They may give same type if meta and para position something is there, molecules are there. They may give functional group region similarity bands, similar bands. However, the fingerprint region they will be different, their fingerprint region bands must be different. So even if they are identical molecules, but like the fingerprints doesn't match, they both will give you different bands in the fingerprint region. Also, we can use the IR spectrophotometry, the measurement by checking the authenticity of a compound. We can study it. The authenticity of a compound can be checked by this. So, besides the frequencies of the signal, their shape, their shape and intensity also provide useful information about the nature of compound that is being studied. Here, I was telling you about this uh, table. Here you can see the IR frequencies of different functional groups. Suppose you have synthesized a molecule in laboratory by seeing some literatures. Literatures means already given literature, or you are having some plan in your mind. You are synthesizing a molecule beautifully, where you are expecting a alcoholic group. Suppose you are expecting that molecules must have a alcoholic group, then you are going for studying getting its IR spectrum. So you are making that compound. You have already synthesized that compound. You are making a palette of it. How will be doing? The paletic technique I have told you how to do the paletic technique. If it is a solid one, it's fine. If it is a liquid one, if it is a gaseous one, the method of sampling I had shown you. So you have to prepare the if it is a solid, you have to make a palette, then put it in the sample compartment. Then your IR radiation is falling on the matter. Then you are going to get the spectrum, IR spectrum. I was showing you transmittance versus your wave number spectrum you are going to get. If it is coming within region of this, then you may predict that okay, it may have a alcoholic group. It may have a alcohol. Sorry, this one 3600. If it is coming within this region, a broad band you are getting 3600 to 3200. then you can confirm, okay, I am having a alcoholic group. If you are expecting alcoholic group to be there, but you are not getting a peak there, you are getting a peak in 300 to 2800, then from there you will get an information that it is not a alcoholic group is there. So your synthesis might be erroneous. Your synthesis has not, you have not done it properly. So in this way you can predict whether your compound is, whatever compound you have synthesized, you are getting it or not. Structural elucidation. If you are synthesizing a molecule where benzene rings should be present, where your benzene ring should be there and a OH group should be there. Suppose benzene ring is there, phenol you are talking about. Benzene group characteristic peak will come about 1450 to 600. So you are getting a IR spectrum where you are getting a peak in between that, as well as you are getting a peak around 3600 through 3200. Then now you are confirmed that okay, my phenol is there because I am getting a characteristic peak for the benzene as well as for the alcoholic peak. So now you are confirmed that your molecule is the one which you are wanting to prepare. Okay. So like this is a chart for you. This is a chart for you, and you can study, so you can do the structural elucidation by using this chart. Okay, that these spectroscopic wave numbers, these frequencies you must remember in order to do it, so that you can predict whether the molecule is the right one or the wrong one, or some impurity has been added to it. That information you can get. For this, so much reading and so much practical knowledge and so much effort you have to put in to the structural elucidation of a organic molecule. Then coming to the quantitative application, in the previous unit we saw that UV visible spectrometry can be used for quantitative determinations. Okay. In case of IR spectrometry, the quantitative use is subject to number of practical and instrumental problems. These are mostly used for qualitative information, structural elucidation. This IR spectroscopy is mostly used for that. Less use is there for the quantitative application part. A number of simple and portable and yet deliverable IR spectrophotometers are also available that may be used to quantitatively analyze a mixture of gaseous pollutants in short span of time, as we are using a all wavelength radiation putting on the sample and getting the results. So these instruments are IR filter photometers and give good results, but not as good as possible for UV visible spectrophotometer. Quantitative parts, you can get more good information in UV visible spectrophotometer. As I was telling you, all spectroscopy has its own merit as well as own limitation too. All molecules you are seeing that it cannot be studied through UV visible, IR, microwave. All molecules you can't study. Certain specific characteristics of that molecule should be there. So coming to the clinical or biomedical application, this IR spectroscopy has been employed for the analysis of several analytes in different biofluids and solid biological samples. This has application in the analysis of pathological samples for diagnostic purpose and also for non-invasive in vitro monitoring. It will not make any harm to the thing. It will not uh, uh, do any harm to the thing. So here the question is, what do you understand by fingerprint region? What is its significance? Understood its significance? Like two similar structural moieties there, they are like twins, but their fingerprint region will be getting different IR spectrum. So this is the summary outline. Many questions are there and many numericals are there. You must practice all these numericals and questions mentioned here. I don't know about your assignment part. Okay, what you are writing here? Anybody from Orissa, Bhubaneswar, all that things. Oh, you are talking these things. Discuss some questions among yourself.
Ma'am,
Okay. Hmm.
I have a question.
Hmm.
Can I ask?
Uh-huh.
Ma'am, why we plot observance versus wavelength in UV visible, but
Hmm.
transmittance versus wave number in IR spectrometry?
IR spectrophotometry. If you are taking the wave observance versus this one, wavelength, okay, mute yourself.
Okay.
It is echoing. Hmm. If you are going to take that, if you see, I closed it. Okay, I'm just opening it. The region of IR, I want to show you that region of IR. This one. So you get a very clarity about this thing. I was just highlighted here. I have already highlighted here. While telling you, I told you. The ordinate, the y-axis represent percentage of transmittance, whereas the axis, x-axis is either you can take wave number or wavelength. You can't take both wave number as well as wave number. It means that it is the position of IR absorption signal presented as either wavelength way, wave number way or wavelength way. But the wave number unit, however, is preferred over the wavelength because an increase in it corresponds to an increase in the energy, whereas the wavelength is related inversely to the energy. Because you just see here, it is preferred over wavelength because an increase in it corresponds to increase in energy, so that the radiation which is falling on the matter, it will get more energy, but it is correlated. However, whereas the wavelength is inversely varies with the energy, you need more energy part. If you see the part of this one I'm just showing you. See, here IR radiations are of less energy. IR microwave, these are of less energy radiations. Okay. If you are taking in terms of wavelength, tuning the spectrophotometer in such a way that wavelength radiation is there, then it may not get a good amount of energy and the signal you may not get a proper way. For the signaling purpose, to get a better resolution, to get a better signal to noise ratio, we are doing that. We are just taking it in terms of wave number and recording it not in terms of intensity or observance, recording in terms of transmittance, which is your log of 1 by t. In logarithm scale we are taking, so that you will get a better resolution of that peaks. Okay. So now we'll move to another part, that is Raman spectroscopy. We'll finish it today also, the Raman spectroscopy. But it is saying an electromagnetic radiation, when passed through a transparent medium, an electromagnetic radiation, when passed through a transparent medium, it interacts with the particle. That particle can be molecule, atom, ions constituting in that. If the dimensions of the particles are equal to or smaller than that of its wavelength, then it undergoes scattering. The dimension of particle are equal or smaller than that of its wavelength, then it undergoes scattering. Okay. It has been observed that most of the scattered radiation has exactly the same wavelength as that of the incident radiation. If so, then this scattering is known as Rayleigh scattering. Yesterday also I was telling you a bit of this, just simply glimpse I told you. But if the scattered radiation has exactly the same wavelength as that of incident radiation, then we say the scattering to be the Rayleigh scattering. However, sometimes what happens, the scattered radiation is found to have lower wavelength or higher wavelength as compared to the incident radiation. That time we say it to be the Raman scattering, and that effect is termed as the Raman effect. This has been given, this concept has been given by Professor C.V. Raman, for which he got Nobel Prize in 1930. Nobel Prize in Physics he got. So here you see the intensity versus your Raman sheet. It has been mentioned in centimeter inverse also for a better resolution. However, it is in terms of intensity, because it is getting scattered and you are getting scattered light, it is of higher intensity you will get over there, but you are putting more energy to it, putting more energy or laser source to it. So Rayleigh scattering, you can see the middle one is Rayleigh scatter, means it is having the intensity the same as that of your incident radiation. Then you'll have some Stokes line and anti-Stokes lines, which are, we say it to be Raman scattering. Okay, so you may note that the intense peak in the center of the spectrum is your Rayleigh peak, and both the sides, the either sides which you saw are the Raman lines. Okay, the lines that you saw in the left of the Rayleigh peak that are having lower wave number value are called Stokes line, and the right side which you have observed in the wave number of higher value are known as anti-Stokes line. So in that way you can calculate the Raman shift. How you are calculating that? From the position of your relic line, how much deviation or shift is there towards left or towards right. Accordingly, you say it to be Stokes shift or anti-Stokes shift. So this is the Raman shift expression. Okay, where mu s and mu 0 are the wave numbers of the source or incident radiation and the observed scatter lines respectively. Okay, so it is obvious that Raman shifts of Stokes lines would be positive, while for anti-Stokes lines it would be negative. So here you see the beauty over here is this, that IR spectrum you are measuring in terms of transmittance, Raman spectrum you are measuring in terms of intensity in the y-axis. You just see the similarity and differences in the peaks. Here you see the fast blue peak you are seeing in IR spectrum. In Raman spectrum it is there in the down, but it is little bit. In IR spectrum, you see the blue long peak is there, but here it is of less intense. And Here you are getting some peaks, however, it is absent in the IR spectrum. That clarity I am just going to tell you in the subsequent part, that IR and Raman spectra of CCl4 you are seeing here. Here you can see the IR spectrometry, that all possible vibrational modes of a molecule may not be IR active. In the previous unit, we saw that only those modes which have an associated range in the dipole moments are IR active. So those are having oscillating dipole moment, they only will be IR active. And so off in the spectrum, while the other modes, other peaks will be absent. So those modes of vibrational modes are IR active, oscillating dipole moment they will have, they are only you are going to get peaks. But Raman spectrum, you will be more clear in the subsequent parts. So in Raman spectrum, only those vibrational modes are active which are associated with change in polarizability. Okay, the one, if you remember the IR spectrum, just a minute, I am taking water. So in IR spectrum, the molecules which are having the change in dipole moment or oscillating dipole moment as soon as the IR radiation is falling on that. So many vibrational modes are there. As we discussed in Deccan, you are having 90 vibrational modes. You may have combination bands, difference bands, forming resonance bands, but you are getting less than 90 peaks for endocrine you may get, because all vibrational modes are not active. They are not resulting in oscillating dipole movement. Wherever you are having symmetric stretching or symmetric bending, moving in a single direction, they will not have a oscillating dipole moment. So resultant dipole moment over there is zero. So they will not. But here for the Raman spectrum, so here the question is which kind of molecules will show you Raman spectrum. So those vibrational modes which are active in Raman active, which are bringing about change in polarizability. So here the question is what is polarizability and change in dipole moment? Here you can see the polarizability is the measure of how effortlessly an electron cloud delocalization or distortion is happening due to the radiation interaction. Okay, how the electron cloud as such, it is polarizing towards this end or towards that end, it is getting distorted by the radiation it is falling on it. Whereas the dipole moment is the separation of positive and negative charge in a system. It is a separation of charge factor it is happening, so it is resulting in the change in dipole moment. Okay, so here the IR and Raman activities of vibrational modes may differ from each other. Okay, and the next part will be more clear. This is a table. Here you can see for water. Okay, for water, suppose you are having here three vibrational modes has been given: symmetric stretching, bending, asymmetric stretching. These three has been given for water. Here the symmetric stretching vibrational mode is IR active as well as Raman active. Here, this is both bending is also active for both the thing, and here also it is Raman active as well as IR active. It is not always mandatory that the molecules which are IR active may not be Raman active. No, it's not that. It can be. but there is some rules for it also. Like the way I was telling you, there is selection rule for it. Every spectroscopy, the radiation which is falling is important. The to get a better resolution, in which way you will be irradiating the molecule is very important to get a better resolution and to get a better signal to noise ratio minimal. Then which kind of molecule you are going to study, which kind of molecule interaction you are studying, that is also important. Then third thing is its selection rule for the spectroscopy is very important. So here what is happening, the molecules which are IR active need not to be Raman active, which are Raman active need not to be IR active, but it may be both active. Okay. Here you can see there is a rule for it. I am just going in the subsequent part. So for CO2, you see here symmetric stretching vibrational mode you are seeing, bending vibrational mode you are seeing, and asymmetric stretching you are seeing. The symmetric stretching, it is IR inactive because you are not having any change in dipole moment. Symmetric stretching is IR inactive. However, it is Raman active. You see, here the bending mode of vibration is IR active. However, it is Raman inactive. It is asymmetric stretching is active, it is Raman inactive. How to guess this molecule is IR active or Raman active? How to guess that? So there is a rule for Raman spectroscopic thing to see in a molecule, that is called rule of mutual exclusion, or you say mutual exclusion principle. The IR and Raman activities of different modes of vibration of a molecule depend on its symmetry properties. Now you are going to inorganic chemistry, where you might have studied the symmetry chapter, the group theory, symmetry chapter, whether the molecule is symmetry or not symmetry. So it is correlated to that. So I can't go there for teaching you inorganic over here. But the thing is, it depends on the symmetry properties. The analysis of IR and Raman spectra of large number of molecules has led to an extremely important general rule known as a rule of mutual exclusion, which states that for a molecule having a center of symmetry, the Raman active vibrations are IR inactive and IR active vibrations are Raman inactive. Here you must remember the molecules which are having center of symmetry, like CO2 structure. Remember the CO2 structure. C will be in the middle, O both side O will be there. It is having a center of symmetry. So this kind of molecule, it is saying the Raman active vibrations are IR inactive and IR active Raman things are Raman inactive. You are seeing this part. Okay, this part you are seeing. But the molecules which doesn't have center of symmetry, then some vibration may be Raman as well as may be IR active. So they may not have a center of symmetry. So today you must read what is center of symmetry. Okay, what is center of symmetry in group theory, symmetric parts or symmetric classes, where one inversion center I also will be there if you are having center of symmetry. So you must go through that part. Okay, so that is not in our context. I am just not going to that part either. So, the polarizability of a molecule and polarization, you may not get confused with these words, polarization and polarizability. Yesterday, I was telling you, you might have remembered, when unpolarized light was going through a polarizer, then you are getting a polarized light. Means the light will be vibrating in all directions. We say it to be unpolarized light. But when you are putting a polarizer, then you are just making that light to vibrate in a single plane polarizer. Similarly, analyzer also will be there, but that will be kept in the after the sample part. After the sample part, the emission you are getting, it will be kept in that side analyzer, so that again you will be getting a polarized light. Okay, but polarization is different. Molecular polarization is different. That is the cloud shifting, electron cloud shifting of a molecule. But plain polarized light or depolarized light, that is related to the light part. Okay, that is plain polarized or that is depolarized. So in general, the symmetric vibration gives a polarized or partially polarized lumbar lines, whereas non-symmetric vibration give depolarized signals. The signals which we are getting, that will be depolarized signals. So, when coming to the instrumentation of Raman spectroscopy, the similar way we studied the IR as well as UV visible, here also for Raman we'll be seeing the instrumentation. There are two main issues with the Raman spectroscopy that need to be addressed by suitable instrumentation. First is, see, the thing is, this sentence you read very carefully, the first sentence. There are two main issues in Raman spectroscopy that need to be addressed by suitable instrumentation. Are you seeing? It need to be addressed by suitable instrumentation. You know one thing, that always research is an ongoing process. What the people do, normally what the scientists do, we are just in a line of lectureship line or professorship line. That line is different, but many scientists in the R&D sectors are there where these instruments are getting designed. What they generally do, the problems, suppose today I am studying a Raman spectrophotometer I am using. I am just occurring certain problems in my analyzing the spectra. Then I am reporting to that instrumentation, that company. Then they will be studying in their R&D sectors. Then to improvise the spectrophotometer, how the suitable instrumentation should be. If the Raman spectrums are very weak in nature, how I should do my optical tuning in the software. Remember one thing, in the software you have to mention you are going to get the thing in wavelength scale, in wave number scale, to get a better resolution. That already fitted software, or you say what to say, that programming, already that instruments is tuned with that programming, how the design should look like and how the signal to noise ratio should be less, how better quality signal you make it. So the it need to be addressed for Raman spectroscopy, Raman spectrophotometry. The first, the inherent weakness of Raman scattering is signal. as compared to the intense of relay scattering. And the second one is about the spectral resolution, the ability to resolve features within the spectrum, how you can tune the resolution, how you can tune your programming in the software or in the instrumentation thing, so that you will be getting a good signal over there. So like your IR's instruments, here also you are having five basic components, that is your laser source, or you can say source of irradiation of the radiation, then sample handling unit, one will be there, then you will have a monochromator, then detector, then signal processing or output device. So everywhere this is the protocol we are maintaining. So if you correlate the things and study, then you can remember most of the things. So you are having a laser source, then mirror, then you are this mirror, or you are putting some filter, or you are putting some polarizer. That tuning parts, that you say as the selectors, means how I want, how what is my wish, how I will teach in my class, whether I should go for a PPT presentation or I should go for this material which is available in the website, which will be easier for the students to access. That is my way of thinking. Accordingly, I will put a mirror, or accordingly I will put a polarizer or analyzer to tune that lights. So it may depend from the teacher to teacher. So it may depend from the spectroscopic tools. It may depend if you correlate in that way. It may depends how good I want to get a good resolution spectrum, how good my signal to noise ratio, that noise signal to noise ratio means signal is up, okay, noise is down, noise is less means you are going to get better signal, okay. So this is a sample compartment. Then the scattered light is covering on a curved mirror. Why here curved mirror has been used? Because all the radiations will not be scattered. Again, they will converge and go into the monochromator. Then photodetector will be there. Then again, your output unit will be there. So this is the way of your instrumentation everywhere. Okay. Sometimes we use grating also. Grating is also very good technique. Last class I just told you grating about. So coming to the radiation source, the way for UV visible tungsten halogen, deuterium tungsten, and for the this one IR spectroscopy, we discussed about that chromium wire, uh, nickel chromium wire, all that things, glamour. So here the radiation source are basically the argon ion, krypton ion, basically the lasers basically used for Raman spectroscopy. The lasers are more intense as compared to normal radiation. This radiation lasers are of more intense beam. It gives a good source of your radiation. So to get a better quality resolution of the emitted spectrum, you may use laser. Okay, so lasers used for Raman spectroscopy must exhibit a good wavelength stability and low background emission. Means background noise or background small emission peaks, that will be avoided if you are using laser, because if you are it is a thing you can say in this way, if your morning breakfast is so heavy, then your full day it will drag it in a good way. If your morning breakfast you are doing in a small amount, then you will be feeling lazy, down all along. So if your ledger source, if you are using, that is of more intense and powerful, then you are going to get a better signal for that. But don't think that you can't use laser for your emission spectroscopy, fluorescence, UV. No, you can't also study there, but lasers are very costly. Lasers are very, very costly. So when we are studying these theories and practical things are also, there is certain limitations in practical part also. We have to see it should be cost effective, it should be affordable. If I have done my research in IIT, that time my facilities are more, here my facilities are less. Accordingly your research you are doing in a different way. So ledgers also we can use there also. Okay, so here ledger source, you are using this ledger source, that is argon ion, krypton ion, helium neon laser, diode laser, indiac laser. Okay, so you can use in different way also by seeing the how good your resolution you are going to get. Then the sample handling device, if you see the sample handling device, then Raman spectrophotometer has a distinct advantage over the IR spectrophotometry. Why you can say that, see, spectrometry you can say, or spectrophotometry also you can say. Nothing wrong in that. You'll be telling why I'm calling every time IR spectrophotometry. Photon, wherever you are using radiation, photon, you can use the phototerm also. There is nothing harm in that. So because it, what I was saying, Raman spectrometer has a distinct advantage over IR spectrometry because it permits the use of the glass for holding the aqueous solution. I was showing you the cuvette. So cuvette is so small, and the quartz cuvette, it is readily available, cheap also as compared to making the initial and KPR, that IR windows. It is very costly, expense. So IR spectrophotometer expense will be more as compared to EV visible. If EV visible spectrophotometer, you can get within 10 lakh also, but IR spectrometer, you can't get within 10 lakh. It is more cost because the parameters, the optical settings involved in it needs more expenses. Okay, needs more expenses. So many universities or many places you won't find IR spectrophotometer much or NMR spectrophotometer. It will be in the selective places. But EV visible you will find in many places. Many places you will find. So cost factor is also a factor over there. Here you are using, you can use the glass holding aqueous solution. That is the best part. The possibility of using aqueous sample is particularly important as it allows ascertaining the water pollutant deciding the biological and inorganic samples. Understood? So wherever you are using aqueous solution, wherever you want to study water pollutant related thing, which is a emerging line of research, water pollution, that time you can use certain spectroscopic tools. You cannot use all the spectroscopic tools. Okay, you cannot use, but you have to be very, very selective. That is what I was telling you. The molecule or sample of study is very important, which molecule or sample you are taking. So this Raman thing is very good enough to study the water pollutants also. Even if this Raman scattering peaks you can get in the fluorescence spectrophotometer also, that is the emission spectrophotometer. You can also get a Raman scattering peak over there. I have also already studied the Raman scattering. Raman scattering, like 1010 wavelength, if you just excite the molecule, then your peak will shift 10 nanometer uh, in the emission spectrum also. So from there it will be clear that yes, my thing is having showing the Raman signaling or Raman scattering thing, because we mostly deal with the aqueous solutions and it is preferred that always you go for the aqueous solution, or if you are designing a molecule, drug molecule which is soluble in water, then it is more marketed, right? If it is you are going to synthesize a molecule which is soluble in organic solvent, then it's okay, but it is its limitations will be there, or its applications will be less as compared to your whatever you are going to synthesize in a water solutions. So the thing is here you are having a detector also. The way I was telling you, photomultiplier tubes can be detectors or photoconductors. Charge coupled devices are also will be there. So basically, these detectors will detect that signaling, then amplifying it, then it will be getting through the output device or output signaling sources. Okay. As far as the application is concerned, this Raman spectroscopy has been recognized as a very powerful analytical tool that is capable of providing information that is not available from other analytical techniques. Okay. Recent advances in instrumentation have made Raman spectroscopy a tool for the choice. Before Raman spectroscopy was not that much immersive spectroscopic tool to be studied. Always the standard spectroscopic tool, basically, which we say normally people use, is UV visible. Then people go for IR and NMR for the structural elucidation. Mass also we use for the structural elucidation. But Raman spectroscopy was not a tool of choice earlier. But now it is also a tool of choice for an increasing number of chemical and biological applications and to study mostly the coordination complexes. Mostly the coordination complexes also used Raman spectroscopy, and that can be used for quantitative as well as qualitative analysis of your inorganic, organic, and biological samples. The qualitative analysis is based on the intensity of the Raman scattered light being proportional to concentration, while the qualitative determination depend on the wavelength shift. From here, what you understood that quantitative analysis means you are going to study how much quantity of the substance is, or how much amount or how much concentration of the substance is. So, from the absorption from the UV visible spectrophotometer, also by using that spectrophotometer, you can do quantitative analysis where you can predict how much concentration of the substance is. Similarly, here also from the Raman spectroscopy, based on the intensity of the Raman scattered line, you can predict the concentration as it is proportional. But I am saying this sentence mean it doesn't mean randomly you can predict. No. Yesterday I was showing you one graph where you are having some reference sample. You must have the reference sample. Then only if you are going for the unknown sample, then you can predict its concentration. Randomly, you cannot move and go and keep the like this barometer or something pressure you are measuring, that you cannot do. Thermometer you are putting in getting the temperature. So it is not like that. you are putting that Raman spectroscopy in the this thing and you are getting. It is not that way. So sample is different, irradiation is different. Then you are going to take a calibration plot. Out of that calibration plot, you have to extrapolate the thing to get a concentration. While this Raman spectroscopy, for the qualitative determination, it depends on the wavelength shift that is being different for a wide range of different molecular vibration. Suppose you are synthesizing a molecule from a parent molecule, then your Raman's peak you are getting at a particular position. Then, when you are synthesizing another thing and taking its peak, but you are finding a shift in that, you are finding a particular shift in that, the IR spectroscopy table, if you remember, there is certain positions for certain groups. So similarly, here also from the wavelength shifts, you can do the qualitative determination, qualitative analysis. If you are expecting at a particular region, but you are not getting in that region, you may also predict, you may get a hunch of the thing that there may be impurity also if you are not getting in a desired position. So the organic compounds contain many functional groups, okay, which is highly deformable electron clouds and are good scatterer of the radiation. Organic compounds, the pi bonds will be there, so more conjugated system it is having, so it is having a good electron cloud, so they can show the good nice way they can show polarizability change, so they can be good system for getting studied through Raman spectroscopy. But if you are taking the hydrocarbons, your electron cloud delocalization won't be much. So that kind of samples are not very suitable for your Raman studies. Okay. So some important functional groups that include alkene, alkyne, cyano, etc. Okay, alkane, it has been not mentioned alkane over here because electron cloud delocalization won't be much. The molecules will not show you a good polarizability. So that are not suitable for studying Raman spectroscopy. So the stretching vibrations of these functional groups give rise to weak or undetectable IR signals. Stretching vibrations will not give you a good IR signal. It may be weak or unpredictable. Whereas in Raman spectra of these, like alkyne or cyano containing group, that molecules are quite strong and can provide useful information about the environment of the group in a molecule. Okay, so by seeing the molecule also, if you go through the net and get questions, there will be given two three compounds will be given. Okay, among these, just tell us which are IR active. Then question will be A will be this, B will be this, C will be this. Okay. Then some questions will be there. Out of this, just tell which are IR active but Raman inactive. So quite often you get this kind of questions if you are preparing for NetGate or if you are preparing for any exams where chemistry spectroscopic tools are there. So further, since the Raman spectrum, we measure the shifts in the frequencies rather than frequencies themselves. Okay, it makes the region below 600 centimeter inverse accessible which is otherwise cannot be explored in IR spectroscopy. See, spectroscopy to spectroscopy, the measurement technique is varying depending on the molecular nature, that kind of molecules, how they are getting better signal or not. Here, you are not studying like the IR spectrometry, you are just measuring in terms of your frequency. Here, you are not seeing that also. If you see the x axis, you are measuring in terms of shift. You are measuring in terms of shift in the frequency. Okay, means you are comparing with a certain reference molecule and you are going for the further thing. Okay, that also you need to understand. But for these things, if you see a book, Molecular Spectroscopy Manual, the complete book is on spectroscopy, Raman spectroscopy and IR spectroscopy. For MSc also, if you have studied already MSc, you will see in a particular chapter or in a particular module, you will have 2 to 3 units or 4 units maximum on each spectroscopy. Raman spectroscopy, complete 10 classes. IR spectroscopy, complete 10 classes. Or microwave or NMR. Complete 10 classes for each thing, because within that so many things are there to know, but in a gist I'm telling you everything to have the idea out of this course which you are studying now, so that it will be beneficial for you later on. Sorry. Okay, so, oh, we have reached here. Then why 15 pages are there? So many questions, numericals, true, false, on that things. Okay, then you can have any doubt, then we can discuss.
Ma'am, I have a doubt. Can we use Beer-Lambert law in any other spectrometry other than UV visible?
Mm-hmm. Beer lumber law, what it is saying? Just tell me, what is that beer lumber saying?
It's telling the relation between absorbance and concentration.
Observance and concentration. Observance is what?
Factors are constant there.
Observance is what?
Uh, Ma'am, we are using observance versus wavelength. I thought,
That is fine. That is fine. Observance is what? Just tell me. From there only, I will just explain it. You will be able to understand.
means it means how much radiation the molecule is absorbing.
But that expression I am asking. Log I zero by I. Okay. Incident radiation divided by your this the radiation which is getting transmitted. Log I0 by I. So Beer-Lambert's law, if you go for the EV visible spectrophotometer, there you will find the reference as well as the sample. Okay. The reference and sample, the output signal you are getting, the output signal you are getting, the spectrophotometer is designed in such a way that it has taken care of that Beer-Lambert's law, and log I0 by I, as such you are getting as the observance. Means that ratiometric technique. It is a ratiometric technique. But
My,
emission, yes,
ma'am,
that is what I am telling. Beer-Lambert's law is meant for the ratiometric technique. It
ma'am,
is meant for the ratiometric technique. However, hello?
Yes, ma'am. Is it
Ah,
applicable to other
no, no,
radiometric?
that is what I am telling. If you are studying fluorescence spectrophotometer, if you are using fluorescence spectroscopy, you can't use Beer-Lambert's law. Why you can't use? Because Beer-Lambert's law is a ratiometric technique which is applicable for the UV visible spectrophotometer. But your emission spectrum, which you are getting through fluorescence spectroscopy, it is not a ratiometric technique. Rather, we are using a certain incident radiation. Then we are monitoring the emission intensity, directly emission intensity. We are not doing anything with the reference. It is not a ratiometric technique. So we can't use the Beer-Lambert's law in that spectroscopy, fluorescence spectroscopy.
So it will be only applicable to UV visible and not
UV visible.
other
Yes.
spectrometric. And ma'am, what is the range of radiations that we can use in Raman spectrometry? Visible, IR,
IR, mostly IR,
but ma'am,
because now,
actually used sunlight as the source.
what?
When Raman started his experiment,
Hmm.
he focused the sunlight with a telescope to
Yes,
conduct his experiment. So,
experiment. Then sunlight is having sunlight is what? White light emission, white light thing, which consists of all the wavelength region radiation, right?
it is, ma'am. I
Huh.
mean, uh, is it uh, any specific light, any specific electromagnetic radiation that he 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 couldn't filter at that time, or it was whole visible range?
It was whole, not visible range. It was um, whole the wavelength radiation. Okay, it consists of sunlight. If you think about infrared, infrared, the hotness we are feeling from a black body or anything, that hotness we are feeling, that is the thermal radiation. That is the infrared radiation.
Yes,
Okay.
ma'am. Our
That
body.
is what I want to say you. So sunlight is consist of almost all electromagnetic radiations. Okay. If you see the Raman spectrophotometry, what we studied now, the source of there is certain source of also radiation. These things, argon ion, krypton ion, all that are the source
When
of
I some
radiations.
argon ion source, then
Hmm.
it ranges from 400 to 400 or
1000. It is
wavelength,
mentioned here.
ma'am.
It is mentioned here.
Wavelength.
488 to 1064.
Yes, ma'am.
Okay. If you go up to visible, it is 800 part.
Yes, ma'am. For
Okay.
400 to
400 to 800. Then your near to this region is your near IR region.
yes, yes.
Near to 1000, it is near IR region. Yes. So basically, these spectroscopic things, when you are dealing with sunlight or that, it consists of all electromagnetic radiations. Consist of all it.
Argon ion.
At the hotness,
So
you are the visibility part from the sunlight, whatever visibility part we are seeing, that is due to your emission phenomena. That is due to emission phenomena, like morning blueness or evening reddish nature. That is due to emission phenomena. Emission phenomena means it will consist of your due to absorption, emission, and scattering phenomena involved in all that part. but the hotness you are feeling out of a body or out of a some energy is there near to that, that is due to IR radiation coming out of.
Ma'am, when we study with the krypton ion source, then it will have 530 nanometer around. Then it will be also in the visible range.
It will be in the visible range. It
Ma'am,
will be
is
in the visible range.
what
Lasers
we also studied.
we can use for the.
So, ma'am, we also studied the vibrational Raman and rotational Raman. Uh, then,
Hmm.
then
In your course it is not mentioned, but
no,
you are having Raman, IR Raman, then this different type of vibrational, rotational
and
Ramans.
combined one pro vibrational Raman.
Hmm. Everything is there, and that too, you will be getting many branches out of that. That PQR branch, if you remember, that PQR
Yes.
branch and Ramans. So many things are there. Many things are there. But the motto of this class or motto of this course is confined to have you all, because see, some are of PG background, some are of UG background. So our motto is to share the knowledge of the spectroscopic method in general, so that UG students also can understand the some parts of the spectroscopy when they go further for the further study. At least somewhere they will recall, okay, during my that course I had heard about this terminology, I can use this terminology, and wherever application is there, you can have a idea about that. So that is the motto of this particular part, because we have to take care of the all the students which are having UG pass out students also. They don't know anything about spectroscopy during UG. So now it is completely new to them. So this is the basic fundamental parts we are studying. But inside that, many things are.
Ma'am, I was just asking on a broad sense that is it ranging from the microwave to visible? We can study the Raman spectrometry from
We can
microwave
study.
to, then
We can study.
can tell
You
that
can give the,
w-
because you are having rotational Raman spectroscopy,
and
which is not in your course.
when the light
But
exceeds vibrational energy requirements, then it will have both rotational and vibrational.
vibrational.
So, ma'am,
It
we
will
can
have both.
the Raman effect or Raman spectrometry can be studied from uh, from a broad range of microwave to
Visible
visible.
to microwave. Here you see this slide. It is very complex. This one also I will teach you in the subsequent classes. And the beauty of this spectroscopy is, what I will say, that it is having a large scale of application. Since so our class constant timing is there and everything is there, we are not able to focus more. Here you see, this is a fluorescence imaging of a neuron. Just imagine neuron. It is having so minute cells. You can study it through fluorescence imaging, fluorescence spectroscopy. But
Selenium
in
75.
you,
So,
what?
ma'am, can we study this fluorescence imaging with the help of selenium 75 isotope?
I don't know. I don't know. I'm sorry, I don't have idea, because many things are there. Okay. And one more thing, why I don't know, I told, because the fluorescence imaging of a neuron, when you are dealing with this, you are also studying a biological sample, right? When you are studying a biological sample, you need to be clear that whether that selenium compound, whether that selenium moiety is suitable for this biological molecule or not. That
Actually,
factors are also there.
actually, madam, for human body, selenium in trace amount is good, but in
Hmm.
high doses it will be toxic.
Okay,
Se-
if you know, then it's fine. So you should actually, practically, you people should know more than me. Okay, so various diverse things are there, various diverse research fields are there, and these spectroscopic tools are very, very useful. But this is as I was telling you, due to time constraint, also we have to focus on certain things. This what we have finished, vibrational we finished, Raman and IR UV visible we finished. Okay. So next class will be seeing the fluorescence spectrophotometry. Fluorescence spectroscopy, then what are the applications of fluorescence spectroscopy, that also we will study. Okay.
Yes, ma'am.
So fine then. So now I think I can stop the class.
Thank you, ma'am.
Thank you. Oh, lab. When will be our labs and exams? Yesterday someone asked me, I forgot his name. His chat is not here. He was asking me about the instrument. About the instrument. Can we see the instrument like that? He was asking. Actually, I will just try to show you whatever is there in my lab. That is fluorescence spectrophotometer is there in my lab. I'll try to show you, but how I will show you? This laptop I will take here to that instrument and I can show you as far as I can, because I have to see the timing of the class also. But practically I can show you that part. I'll try to show you. I will find some time for that so that I can show you how to record the sample over there, or how the light is passing through that part I can show you. Okay, that also. And when will be your labs and exams, sorry, I'm your just counselor and teacher, your coordinator, the regional center you can contact. They can tell you when is your labs or exams. Okay, thank you.
Thank you,
Thank
ma'am.
you. So I am stopping my.
Thank you, ma'am.
Thank you, ma'am.
Thank you.
Thank you, ma'am.